Hello and welcome to SST Chemistry channel. Today we are going to discuss a topic which will be of little use in chemistry subject to a class 11 student. But yes, so far as the curiosity of a very promising student is concerned, he or she will be definitely feel little happy to know why there is a splitting of spectral line in the presence of magnetic field, what we call the Zeeman effect, or in electric field what we call the Stark effect. Why there is a splitting? So I thought of making a video on the Zeeman effect, and the headline, the title of this topic is Fine Structure in Atomic Spectra. The fine structure. Why a single line is split into 2 or 3 or more finer lines called multiplet. If 2 finer lines, it's called a doublet, 3 triplet, 4 quartet, 5 quintet, and so on. In general, it is called multiplet. Why? Now you know in hydrogen spectrum, say for example in Bohr's the Balmer series, which produces few lines and they go for a convergence at the lower wavelength region. The first line, which is falling on the orange region, as due to the transition from n is equal to 3 to n is equal to 2, that transition gives one line. That emission, one photon, one line. But under which condition that one line will be split into 3 lines or 2 lines or many lines, that we are going to study here. If it is in magnetic field, it is Zeeman effect. If not, then what effect? I'll tell you. Without magnetic or electric field, there can be also splitting of spectral line. So all these together as a whole we shall be discussing in this video. Let's start. This is the 16th video. The 15th video on atomic structure was just now complete. That is the exotic positronium particle. And here we will be talking about spectra, atomic spectroscopy, the splitting. Now, there are 2 types of splitting of spectral line. One, in the absence of external magnetic or electric field. That's very surprising to us. If you are a beginner, then you only know that splitting of spectral line can happen in presence of only external magnetic or electric field, Zeeman and Stark. But no, even without Zeeman or Stark effect, you can get the splitting of lines. So one case is absence of external field, and that the reason behind this is what we call spin orbit coupling. We'll discuss about that. Spin orbit coupling. And this is under high resolution spectrometry. I'll tell you what is high resolution spectrometry and what is low resolution spectrometry. Everything in details. To the extent that it will not be monotonous to a class 11 or 12 student or a usual viewer who is interested to know the concepts behind the splitting of spectral lines. Now, the other way to find the splitting is Zeeman effect or the Stark effect in presence of external field. And there are 2 types of Zeeman effect. One is the normal Zeeman effect, that is under low resolution spectrometry. and there is no spin orbit coupling, low resolution spectrometry. And under high resolution spectroscopy, in the presence of magnetic field, that would be called anomalous Zeeman effect, where splitting due to two reasons. One, due to spin orbit coupling, we do not know, don't worry what is spin orbit coupling, and one due to magnetic field, the external magnetic field. So there will be two splittings occurring together, but in a conjoint manner. I will know about that, don't worry. So let me tell you, this is a simple sketch profile of atomic spectroscopy, where you are atomizing a particular element, say sodium. A nebulizer is not the medical nebulizer, it's an atomizer, right? That it converts the sample, supposing in its liquid form or solid form, into its vapor, and it injects to the flame where it burns, where it goes to the excited state, and then while it will return back to the ground states or the lower levels, then it will emit radiations, and we can see after resolution or splitting into the monochromatic radiations by using a monochromator or a prism or a grating. Now see, here is the sample which is vaporized, which is emitting radiation. This is a hot spectrum, emission spectrum. Supposing it is sodium spectrum, it is sodium vapor giving yellow flame. But how to push the flame into the monochromator, which is a prism? For you, it is just a prism which has the capacity to disperse the individual monochromatic radiations which are present in the mixture. Split them into individual monochromatic radiation, and then the detector will detect them individually. It will show you in the form of lines or a graph. Nowadays, you are getting a graph, ready-made graph available in the monitor. You can have a look, or you can view through a camera, right? So this is a detector, and this is the real separator, monochromator, or a prism or a grating. The advanced form of prism is a grating, diffraction grating, where the resolution power is more than prism. Understand? So this part is the main component of the spectrometer, which will resolve the mixture of radiations, polychromatic mixture, into individual, just like Bezier from the solar spectrum. The same way, whatever will be there. Supposing sodium vapor yellow flame contains only two monochromatic radiations. As you know, these are called D1 and D2 line, one at 5,890 angstrom, the other one 5,896 angstrom, D1 and D2. So these two will be separated here, and you get two lines, yellow in the yellow region. If you view it through a camera, or you put a screen, because it is a visible spectrum, you can get the observation either directly by your eye, or you can take a photograph and then see. And this is a hollow cathode lamp which is used, electron beam is used to push the flame. It doesn't produce any radiation, no visible radiation or any other electromagnetic radiation, but it is there to push the flame in a very concentrated manner to fall on the monochromator. Now, this is the most vital part of a spectrometer, which will resolve the individual monochromatic radiations from this mixture, and this will detect the spectrum. It will give you the spectrum, right? Now this is ordinary, there is no magnetic field here, right? But here you have two possibilities. whether you get a low resolution spectrum of the same plane or same radiation, or a high resolution, depending on what monochromator you are using. Is it a powerful resolving agent, resolving substance like a grating, diffraction grating with high power capacity, or ordinary prism? So I am not going to talk more about how you can increase the resolving power of this monochromator, but remember, when we say the spectrum is taken under ordinary resolution or low resolution, that means the power of this monochromator is not much. But if it is a high resolution spectrometer, then here we make the manipulation. You replace some other monochromator like a diffraction grating or more powerful separators or monochromators, so that it has the power to split the radiations which are varying from each other by very, very small value in terms of nanometer, not in terms of angstrom, even lower than that, right? So, but in case of Zeeman effect, you have to put a magnetic field here in this. Now see, this is a Zeeman effect spectrophotometer where an external magnetic field, now this is the North Pole and South Pole. Nowadays electromagnets are used, where by increasing the current you can increase the magnetic field strength, and you can switching off the current, you totally make the spectrum go out of Zeeman, or magnetic field will be zero. So in this equipment you can see ordinary spectrum without any magnetic field, but here this is the place where you have a monochromator. By changing the capacity of this part, which is inevitable in every spectrophotometer, you can say whether it is a low resolution spectrometer or a high resolution spectrometer. You understand? This is the main component of the spectrophotometer. But this magnetic field is an additional feature to see Zeeman splitting or stark. I mean, it is an electric field, then it is stark splitting. Zeeman is magnetic field. Now you remember two things: one here, the other here. One here, the other one here. If there is no magnetic field or electric field which is encircling or engulfing the sample, sample will be kept inside, in between the two poles of the magnet. If the sample will be in the vapor form, in atomic form, it will be kept, right? And if there is no magnetic field, just switch off, no current. So that is an electromagnet. So there is no current, no field. Then it is ordinary spectrometer. But that ordinary can be converted to low resolution or high resolution depending on what monochromator, what kind of monochromator you are using. Is it an ordinary one or a very sophisticated one, right? So two things are to be controlled here. That is low resolution, high resolution. And one thing will be controlled here: magnetic field, no magnetic field. If magnetic field, Zeeman. If no magnetic field, no Zeeman. But here we can have two possibilities. Got it? So I have written here that there are two types of splitting. I mean, splitting of spectral line, one into multiplet, one into doublet, one into triplet, or so on, is possible under two situations. One, in the absence of magnetic field, no Zeeman, no stark. In that case, it is due to the spin orbit coupling, LS coupling. Wait, don't worry. And that happens only under high resolution condition. That means here you have to improve the capacity of the separator or the monochromator here. That is under our control. Whether you are using a high power grating or a low power prism, is under our control. and the other one is in the presence of external field. And in the presence of external field, we have also two possibilities: either low resolution, where there is no spin orbit coupling, normal Zeeman effect, that we call the normal Zeeman effect. And if we use a high resolving power grating or a separator or a monochromator, then it is anomalous Zeeman effect. The splitting due to this will be combined in a very interesting manner to give you the splitting pattern, completely different from those which you have only high resolution spectrometry, no magnetic field. But with magnetic field, the number of lines will be increased further. Let's proceed further, right? Now let me read out, which I have already told you, just for the sake of completeness, formality. Let me read out, but just you listen to me. Look here. When the radiating sample is kept inside an external magnetic field, inside magnetic field, and its emission spectrum is analyzed, then each spectral line was found to split into a few finer lines, which is called a multiplet. This is Zeeman effect. The H alpha line, that is the first line of the Balmer series in the orange region, the H alpha line in the Balmer series for the transition of electron from 3 to 2 gives 3 lines, which is a triplet in presence of external magnetic field. Don't worry, we will be knowing how these 3 lines are produced. What is the logic, principle behind this? We'll know. Similarly, if electric field is used in place of a magnetic field, we will be getting similar effect, that is called Stark effect. In fact, Zeeman effect is observed at low external magnetic field. The magnetic field strength should be low. At high field strength, there is splitting, no doubt, but Zeeman calculations, Zeeman rules that Zeeman has propounded will not be applicable. That will be a different effect, that is called Paschen-Back effect. And we will not be discussing that. The Paschen-Back effect is not the topic of today's discussion. We'll be using only the Zeeman effect, which makes use of low external field strength. And in fact, during the time of Bohr, when splitting of spectral line occurred in presence of external magnetic field, Zeeman effect was recorded, was observed during the time of Bohr. Then Sommerfeld proposed that yes, each principal energy level is definitely associated with some sub-energy levels or subcells, right? And then the idea of elliptical orbits came to the mind of Sommerfeld, who modified Bohr's theory, and we did discuss that in our previous one video we have done. But that has been obsolete when the quantum mechanics came into being. Sommerfeld theory is not in practice, in vogue, right? Now, the presence of sub-energy levels, in fact, that was evidenced from the Zeeman effect, right? Now, I saw you just in the beginning that one line, that is the orange line in the Balmer series, without external field, without any external field, you are getting one line, and these are circular lines, forget about it, right? So those are interference patterns, interferograms, so we forget about those details in our optics program. So you talk about one line in the orange region, that is the H alpha line, splits into a triplet, 3 equally spaced, equidistant finer lines. Here I have magnified into 3 widely spaced lines, but actually they are spaced very close to each other. Very close to each other. These are called fine lines, and we get 3 lines. this is at this position at the middle, and this is delta lambda to the left, delta lambda to the right. So there will be 2 delta lambda from the first line to the last line, right? So this is a triplet. In presence of external magnetic field, the line splits into a triplet. This is Zeeman effect, right? One line, now in presence of external field, 3 lines. Now I have already told you, so I can save time, that Zeeman effect is of 2 types. One is normal, means what? Can you tell me? Normal Zeeman effect is shown when there is a resolving power is low resolution, when there is no spin, no unpaired electron. More correctly, if the atom doesn't have any unpaired electron, no resultant spin, no net spin, that is called a singlet to singlet transition. Don't worry, we'll talk about that. Or under low resolution spectrometry. And that happens in fact at, you can write down at, or under low resolution spectrometry. What I want to say, that if an atom like hydrogen has 1 unpaired electron, or an atom like sodium which has also 1 unpaired electron, that there is a spin, that a net spin is S is equal to plus half. If there are 2 unpaired electrons, like in the case of carbon in the ground state, or in the case of titanium, 2 unpaired electrons in the D. So if there are 2 unpaired electrons, net spin will be half plus half is equal to 1. That is a total spin. So if all the electrons are paired, then there is no spin orbit coupling. I'll tell you, the spinning of electron will not have any impact on the splitting of a line, because the 2 are balancing each other. One magnetic field is cancelled by the other because it is paired. So the assembly of a pair will not have any magnetic influence on the surrounding. So only when there is an unpaired electron, 1 or more, then only that will influence the magnetic property of the orbital, and in the presence of external magnetic field, the entire quantum levels will be non-degenerate, will be different from each other, right? Splitting will occur in that case. If there is no unpaired electron, so it will not show any spin orbit coupling, and always it will be normal Zeeman effect, whether under low resolution condition or high resolution condition. But if there is an unpaired electron, 1 or more, then under low resolution condition, that means using an ordinary prism, then that will not be able to split such fine small energy difference which the 2 different spin states, clockwise and anti-clockwise, will produce on the quantum levels. It will not be detected. So when you use a low resolution condition, even if there is 1 or more unpaired electron, that comes under normal Zeeman effect. Here we'll be using the magnetic field, no doubt, but here we'll be using low resolution, ordinary prism. Right? In that case, spin of the electron will not have any impact to change the magnetic property of the orbital, and hence the splitting of a line. And the other one is anomalous. There is magnetic field. There is magnetic field means Zeeman. No magnetic field means no Zeeman, right? And here it will be high resolution. You are using a high power diffraction grating. I am not going to tell you what is a grating and how it is different from a prism. I'm not going to discuss that here. So where there is 1 or more unpaired electron, yes, unless there is an unpaired electron, there cannot be any anomalous or any spin orbit coupling. If all the electrons are paired, even if one electron gets transited to the higher energy level, but it continues to remain in the same spin configuration. Supposing here it is clockwise and the other one is anti-clockwise, it will be promoted to the higher energy level, the excited state, with the same anti-clockwise spin. So that is called the singlet state, where the spins are paired. So whether it remains in the same energy level or a higher energy level, but so far as the pairing of spins are concerned, it is paired and there is net spin is 0, so it will not be influencing the magnetic property of the orbital, and hence the magnetic strength and external magnetic field will not be influencing the energy states of the orbital in any way. So if there is one or more unpaired electron and you are using high resolution spectrometry, here you are using a grating, that case, yes, the splitting will be influenced also by the spinning electron, the unpaired spinning electron. That can have two possibilities, clockwise and anti-clockwise, which will slightly change the energy levels, which was undetected in low resolution condition, but which can be resolved under high resolution condition, and that is called anomalous Zeeman effect, right? Now, first let me introduce just how we can get splitting of spectral line in the absence of external magnetic field. That is due to spin orbit coupling. Just let me introduce before we start Zeeman. Let's say there is no Zeeman at all. The splitting of spectral line under high resolution spectrometry, but no external field. This is not given, this one, but we'll be using high resolution here, taking a grating in place of a prism. So we do that, then let's see what happens really. Each spectral line, there is no Zeeman effect, but still there is splitting. Let me first introduce that. Each spectral line, I think you remember while you study the demerits of Bohr's theory, one of the demerits was that under high resolution spectrometry, each line was found to split into a doublet. It's not really a doublet every time. Again, it will be split into a few finer lines. Some cases it is doublet, right? So that we are studying. No magnetic field, no Zeeman, but under high resolution condition where the splitting power is very pronounced using a high power diffraction grating. That case, what happens, each spectral line of hydrogen was found to give finer lines under high resolution spectrometry. For example, the L-alpha line of Lyman series. You know what is Lyman series? It is due to the transition of electron from higher levels to the first cell, right? 2 to 1 will produce the first line, that is called L-alpha. 2 to 1 transition will produce L-alpha. That line was found to split into two finer lines, what we call a doublet under high resolution condition, right? Obviously, you must have guessed that this splitting into a doublet is due to the two possible spin states. One coming from the higher level with, say, anti-clockwise spin, and the other possibility coming from the higher level in clockwise spin. So these two transition energies are slightly different, even if there is no external magnetic field. We'll note about that, right? This happens when there is a net spin. Net spin is non-zero. At least one unpaired electron has to be there. Even if you use high resolution, if the spins are all paired and the electron is excited with the same spin, the pairing is there, is maintained. This is called the singlet ground state. This is the singlet excited state. The excited singlet, this is the ground state singlet, but singlet state continues. In that case, there is no question of further splitting. But the atoms like hydrogen, which has one unpaired electron, the atoms like sodium and the like, they will show splitting under high resolution condition even without magnetic field or electric field. And this happens when the net spin is non-zero, and it is due to the two different spin states, spin up and spin down, with respect to the internal orbital magnetic dipole arising from the orbital angular momentum. We'll know about that. Don't worry. Don't go away anywhere. Just like TV anchors, they always try to glue with the viewers by intermittently telling, don't go away anywhere. More breaking news is coming. That is their strategy, how to glue with the viewers. So I am saying that don't go away anywhere. We will be knowing why this spin of the electron is influenced by the orbital angular momentum. If the orbital angular momentum is zero, like s-orbital, then there will be no splitting at all. Because I'll tell you, just hold on. This is called fine structure splitting. When there is at least one unpaired electron, which has got two possibilities, spin up and spin down, and moreover, it's not an s-orbital, it is a p orbital, because p orbital has a resultant angular momentum, orbital angular momentum. We'll talk about that, don't worry. In that case, you will find there is an influence where this spin up and spin down, they will be influenced by the internal field produced by the motion of orbital, the motion of electron cloud, electron motion in an orbital, right? Let us proceed. See how slowly and steadily your concepts are getting consolidated more and more. But don't go away anywhere. Try to focus your brain only to what I am saying if you are interested. And I really want that a physics person who is the real expert in this field. This is nothing but atomic physics. And we are borrowing some knowledge from the physicists in the domain of atomic physics to teach students. Of course, I'm sure I have already crossed my boundary, but still I want some physics expert in the field of atomic physics should watch my video and should give a comment whether my experience with little bit of spectrometry had some flaw in it, right? Please, you can ask, if you are a student, you can ask your physics teacher who teaches you atomic physics to watch my video and give a critical comment on what I am saying. Right? Now see, this next one, it is due to why there is a splitting. There is no external magnetic field, but still there is splitting. Why? It is due to spin orbit coupling, or what is called LS coupling. L is the angular momentum vector, we'll talk about that, of the orbital, and S is the spin quantum number or spin angular momentum vector. So LS, or also sometimes called RS, due to the two scientists, Russell Sanders, RS coupling, discussed later. Because in this video, part 1, this is part 1. Yes, I didn't tell you that this is part 1, and there will be part 2, where we'll be discussing in detail about spin orbit coupling. Don't go away anywhere, right? But in this video, the primary focus will be on Zeeman effect, without any spin orbit coupling, normal Zeeman effect. In the second video, we'll be talking in details about spin orbit coupling, and then the anomalous Zeeman effect, right? Yes, this we have done it. And yes, this is due to the spin orbit coupling or LS coupling. Species like hydrogen, sodium having an unpaired electron gives this effect. Without magnetic field, if you are getting a multiplet, by using just high resolution spectrometry, changing from an ordinary prism to grating, high power grating. In that case, you are getting a multiplet, means it has one or more unpaired electron. Then only the spin will couple with the orbital angular momentum. Just hold on. This is sometimes called internal Zeeman effect. I will be refraining myself to use the term internal Zeeman effect only to avoid arousing confusion in you. Zeeman effect is Zeeman effect, but the spin orbit coupling and the splitting of a spectral line due to that is sometimes called internal Zeeman effect. It is very, very scientific, because the external field was trying to split in Zeeman, but here the internal field is the orbital angular angular momentum dipole moment vector. We'll talk about that. That you have to think as if it is an external field to the spinning electron. The spinning electron will be influenced by the internal field produced by the orbital motion. Let's see what's that. Single line, say L alpha line in the Lyman series, and our high resolution spectrum keeps two lines, right? No Zeeman. Now see, let's now officially discuss how many types of motions are there inside an orbital, and what are the two different angular momenta. The plural of momentum is momenta. So the electron can have two types of magnetic fields. One due to the orbital angular momentum, and the other due to the spin angular momentum. And let's first start orbital angular momentum. And you already know that the orbital angular momentum is found out by this expression. Capital L, the orbital angular momentum, is small l into small l plus 1. There is a bracket, the parenthesis, half of it is missing. I will make it all right. Right? L into L plus 1, root over, then h cross, or h by 2 pi. So L is azimuthal quantum number. If this will be 0, then it will be 0, all will be 0. So the orbital angular momentum of an s orbital is 0. Very, very, what we can say, unconvincing. It is a paradox, unconvincing. I'll tell you, for all s orbital, the orbital angular momentum is 0. Only when it is a p orbital, doesn't matter whether it is 2p or 3p, any p orbital, this is 1, this is 1, 1 plus 1, 2, root 2 into h by 2 pi. If it is a d orbital, then it is 2, 2 plus 1, 3, 3 2s are 6, root 6, h by 2 pi, and so on. Right? So this angular momentum is due to the orbital motion. The orbital motion of electron is the electron cloud, which is taken to be a standing wave around the nucleus. If the orbital angular momentum is 0, then it is undoubtedly an s orbital. Why? It's very, very difficult to conceptualize, but I have tried myself. Any attempt to conceptualize why the s orbital has 0 orbital angular momentum will lead you to frustration. But I have tried to tell some explanation that, you remember psi, the wave function, or the radial function capital R versus radial distance r. That graph for any s orbital starts from the highest value at the nucleus and it goes on decreasing. So unlike p and d, the electron density is maximum at the nucleus and goes on decreasing exponentially. Right? And moreover, there is no angular node. So it is independent of angle. So the accumulation of electron density, the electron cloud, in a symmetrical manner, in a spherically symmetrical orbital, will cancel out. The net angular momentum will be 0. The net angle, it's not a particle in wave mechanics. Electron is not a particle. It's a smeared electron cloud. So the resultant effect is 0 for an s orbital because it's spherically symmetrical and it is concentrated nearer to the nucleus more and it fades out. I mean, it decreases as you go to higher and higher radial distances. So psi is maximum at the nucleus for an s orbital and there is no angle dependence. Therefore, the resultant angular momentum vector is reduced to 0 for any s orbital. So that means it doesn't produce any magnetic field. S orbital doesn't produce any net magnetic field. Now, there will be two types of magnetic fields. One due to orbital motion, which is absent. The net motion is 0 for s orbital, but p, yes, it is angle dependence is there. And the psi value is 0 at the nucleus and it goes on increasing and then decreasing. So it is the net angular momentum is non-zero. It is root 2 into h by 2 pi for p orbital. It is there. It is non-zero, right? So in that case, that produces a magnetic field. So every spinning and the spinning electron, the unpaired spinning electron is like a bar magnet. So there are two magnets. One a bigger magnet, which is circulating electron cloud, that is the orbital angular momentum that produces the orbital angular dipole moment, magnetic dipole moment, the orbital angular dipole moment, magnetic dipole moment due to orbital motion, and that is due to orbital angular momentum, L into L plus 1 root over h by 2 pi. The other one is the spinning motion. So one tiny magnet and the face of that little larger magnetic field. So the larger magnetic field of the orbital motion will influence the tiny magnetic field produced by the spinning unpaired electron, right? Never correlate between classical angular momentum given by Bohr's theory, that is simply nh by 2 pi or nh cross. But here it is L into L plus 1 root over h pi. So don't correlate between the two. While this is used for calculation of energy, this is used for the calculation of magnetic dipole moment. So this has more mathematical meaning than physical, right? So any attempt to correlate between the classical Bohr's angular momentum, which is nh by 2 pi, with the wave mechanical angular momentum will lead you to frustration. That is different, used for only energy purpose, and that is in classical mechanics. But in wave mechanics, classical quantum theory, not mechanics. Quantum mechanics also has principal quantum number n from the Schrodinger's wave equation also. And also energy term, energy calculation using the Schrodinger's wave equation, right? So then I'm showing you there are two types of magnetic fields. One due to orbital motion. This is orbital momentum and hence a magnetic field. And this is a spinning electron, also a magnetic field. So this is a tiny magnetic field. This is a bigger magnetic field. So they will interact with each other even if there is no external magnetic field. So the internal influence with each other, that will produce two energy levels. I'll tell you, just don't worry. Don't go away anywhere. Now, what is spin angular momentum? I have already told you that while having an orbital motion around the nucleus, it is also spinning, producing another magnetic field, the spin magnetic moment. Or the corresponding momentum is spin angular momentum, which is given by s into s plus 1 root over h by 2 pi, right? So, or it is n into n plus 2, the bracket is missing. what is S? S is not always half. Yes, if there is only one unpaired electron, S is half. But if there are two unpaired electrons, half plus half is equal to 1. Here is the net spin. It is the net spin quantum number, which is sometimes called total spin, obtained from all the unpaired electrons. The electron pairs are not taken into consideration. So there always this S is always an integer, a positive integer, 0. If there is no unpaired electron, it will be 0. There will be no spin magnetic moment, no spin angular momentum. Hence, there is no magnetic field from the side of spinning. There is no net spinning because they are cancelling each other. If one is spinning clockwise, the other one is spinning anti-clockwise. So there is no net spinning magnetic moment or spin magnetic moment, right? So 0, no spin effect, and half, 1 unpaired electron, 1 for 2 unpaired electrons, 3 by 2 for 3 unpaired electrons, and so on. Half for each unpaired electron. And if you do not like to use this equation, this relation, you can take n. N is the number of unpaired electrons. N into n plus 2 root over h by 2 pi. This will give you the spin angular momentum, the net spin angular momentum. This is due to the spinning motion of unpaired electron or unpaired electrons, which produces spin angular momentum and hence spin angular magnetic dipole moment. So there are two magnetic fields. So if the orbital motion is not there, net resultant motion is 0. That means the angular momentum of the orbital angular momentum, capital L, is 0. That is for s orbital. But there is a spin, then the only one magnetic field is left out. There cannot be any internal LS coupling will not be in that case possible. So LS coupling is possible for p orbital, d orbital, not for s orbital, because there is no orbital magnetic field to influence the spin magnetic field. In case of s orbitals, the net magnetic field is produced only by the unpaired spinning electron. If this orbital is completely filled, spin paired, then there is neither orbital nor spin momentum in that state. For example, ground state of helium. Helium has 2 electrons, 1 is 2. It's paired. I'm talking about ground state, not talking about its emission spectrum, ground state. So it is a paired one. And even if one of the electron will be excited, if it remains in the same antiparallel configuration, then net spin is still 0. So in the s orbital, if it is there, the net orbital motion is 0, capital L is 0, and the net spin is 0 because plus half minus half that get cancelled. So there is absolutely, in the ground state, there will be no magnetic field. But if there is one unpaired electron, then undoubtedly there is a magnetic field, and that is due to spin magnetic field, not the orbital. But now see the comparison between the classical Bohr's theory and the wave mechanical model of atom. In Bohr's theory, people will say the magnetic moment of electron in the s orbital, that is the first cell, is due to the motion, electron motion. MBR is equal to nh by 2 pi. Whatever the equation you may give, doesn't matter. It is due to the electron motion, revolution, circulation about the nucleus. But in wave mechanical concept, this magnetic field or magnetic moment is due to the spin. It is due to the spin angular momentum vector, because the orbital angular momentum for any s orbital is 0. Now look to the difference. Same concept, outcome is same, that the electron has a magnetic field if it is unpaired. But classical Bohr's theory will say, because it is circulating around the nucleus, so it is having some angular momentum and hence a magnetic moment vector. But in case of wave mechanics, they will say it is due to the spinning motion of the electron. That is due to spin angular momentum, the magnetic dipole moment arises, not due to orbital motion, because for any s orbital the orbital motion is 0. I mean the orbital angular momentum vector is 0. Now we will be now coming to Zeeman effect. After this we will be focusing on the Zeeman effect. So far we have been discussing the two types of angular momenta. In the meanwhile, we have already discussed that there can be spin orbit coupling in p orbital, not in s orbital. S orbital will have only one unique state. Will not, the details will be doing in our next video. Hold on for a moment. No, don't consider about spin orbit coupling. Only consider there are two types of momenta: the angular momentum of the orbital angular momentum, that is capital L, which is small l into L plus 1 root over h by 2 pi, and that generates a magnetic dipole moment. This is orbital dipole moment, orbital angular dipole moment, magnetic dipole moment, and that is 0 for s orbital. And there is another spinning angular momentum, and hence a spinning magnetic dipole moment, right? So that happens when there is an unpaired electron. Then we will be focusing only on normal Zeeman effect. What is normal Zeeman effect? When there will be a low resolution spectrometry, irrespective of whether there is an unpaired electron like hydrogen or sodium. I am not talking about high resolution. If the resolution is resolving power of the monochromata is poor, in that case, even if there is an unpaired electron, there is a spin magnetic field, but it has, it will influence, it has influenced, but such splitting, such small energy separations cannot be separated by the separator or the monochromata. So the normal Zeeman effect is observed when the resolving power or the resolution is low and there is an external magnetic field. Now we come to the external magnetic field, right? The internal magnetic field, due to the orbital motion, we have assumed that there is no spinning motion. We have assumed that the spinning motion has no effect under low resolution condition. The internal magnetic field due to orbital motion, that is capital L, interacts with the external magnetic field B0 or external magnetic field, which is applied in a fixed direction. North pole, south pole is kept fixed, as you have seen in that picture. So that the direction of the external field is fixed, and that field will interact with the orbital angular momentum. So they will exchange energy and hence split the energy levels into more than one states. Thus the degeneracy of orbitals, the 3 p orbitals, the 5 d orbitals, even the degeneracy of subcells, SPD, they also will be non-degenerate, particularly for hydrogen-like atoms, when there is only vacant cells and subcells. But in multi-electron species, because there is the penetration power will be different for SPDF, so their energy levels are themselves non-degenerate. But in hydrogen-like species, where there is no multi-electron, with one electron, in that case, the external field not only makes the orbitals belonging to a particular subcell non-degenerate, but also first the subcells belonging to a particular cell also become non-degenerate. 2s, 2p will be of different energy. 3s, 3p, 3d are of different energy, even if there is no more electrons there, like sodium atom, which is 1s to 2s to 2p, 6, 3s, 1, right? In that case, there is only net orbital momentum. That is only case of p, d, f orbitals, not s. S doesn't have any L vector. Capital L is 0 in magnitude. If there is only net orbital momentum, that is the case with p, d, f orbitals, and no net spin, then each subcell is split into 12, or if there is a spin, then it is under low resolution condition, the spin effect will not be observed. In that case, each subcell will be split into 12 plus 1 non-degenerate orbitals. If it is p, then 2 into 1 plus 1, 3. You already know Px, Py, Pz, they are degenerate. But the moment external field will come, they will become non-degenerate. And if it is d, there are 5 orbitals. You know, dxy, dyz, dzx, dx square minus y square, dz square. They are degenerate, having same energy value. But the moment external field will come, the interaction between the external field and the external field is in a particular direction. And the orientations of the different d orbitals are different. So they will interact to different extents to have different energy values. In the same subcell, the energy values of SPDF will be, SPD, for example, it is in the case of, no, I'm so sorry, the 3p orbitals of p subcell and the 5 d orbitals of d subcell, they will be different from each other. Supposing d orbitals have 5 magnetic quantum numbers, -2, -1, 0, +2, +1. All of them will have different energy values, right? So F subcell is split into 7 non-degenerate orbitals. Now see, thus single transition energy is converted into multiple transition energies, because there was only one. All the 5 d orbitals were of same energy. So a transition from 3d to 2p, for example, that was unique. But here there will be 5 d orbitals, one above the other, of different energy values, and there will be 3 2p orbitals. So the transitions will be 5 into 2, 10 different transition energies will be involved, right? So thus a single transition energy is converted to multiple transition energies, resulting multiplet structure or fine structure of spectral lines. Can you tell me what we are talking about now? Is it Zeeman effect or no Zeeman effect? Only splitting. It is Zeeman effect, splitting by Zeeman, and no spin orbit coupling. We have taken low resolution condition, right? Low resolution condition, there is no detectable spin orbit coupling. Although coupling is there, but it's not detectable. The gap or spacings between the adjacent fine lines in a multiplet is same in this case. Equidistant, equally spaced, which is directly proportional to the applied strength of the magnetic field. More is the strength, more is the separation between the adjacent fine lines in a multiplet. For example, H alpha line of Balmer series gives a triplet under Zeeman condition, Zeeman effect. Under low resolution condition, there is no anomalous, because there is one unpaired electron under high resolution condition and Zeeman condition. These 3 lines will be split into many other lines. We are not discussing that. In this video, we are going to end very soon. It is only speaking of low resolution Zeeman effect. Low resolution. Here, resolution is here. Zeeman is here, is field. You understand? Zeeman is the field. And resolution is here. It is the intrinsic component of the spectrometer. And if there are 2 lines in a multiplet, we call doublet. 3 lines, we call triplet. 4 lines, a quartet. 6 lines, sextet, and so on. Now, I have shown you that one line of the Balmer series, the first line, the H alpha line of the Balmer series, in the presence of external magnetic field, will be split into 3 equally spaced, equidistant 3 lines. This is this one, the same wavelength, but there will be one with a plus delta gap to the left, the other line to the minus delta to the left, and the other line plus delta to the right. So there will be 3 lines. This is Zeeman effect, 3 lines. But you might be wondering how this has happened. There are so many transitions. Supposing transitions occur from 3d to 2p, for example. There are 5 different d orbitals, and there are 2 different p orbitals. So there are so many possibilities. 5 into 2, 10 different transitions. Now how come you are getting only 3? What has happened to the other 7? I'll tell you about that. They have gone to heaven to play with gods and goddesses, right? Wait. Now, same thing I have shown, only one line I have taken. This is the famous Balmer series, normal Balmer series, no high resolution, no Zeeman, nothing. No Zeeman, no high resolution. High resolution also it will be split into 5 lines, I'll tell you about that, right? High resolution, no Zeeman. But this is only Zeeman under low resolution, Zeeman under low resolution. That is called normal Zeeman effect. Right? So this line also will be split into a multiplet. But I am only talking about this orange line, which was a single line in a low resolution, no Zeeman effect. Under Zeeman effect only, same no resolution, will be getting 3 lines. This is normal Zeeman effect. And I am showing you. I am showing you before we complete this program. Another 15 minutes to go. We will wind up, and you must make sure that you will be watching my next video immediately after, not give more time, because in the next video I will be at the end, I will be asking you a few questions, review questions. We will be summarizing everything so that these complicated things which I am going to present before you will be completely imprinted in your brain, right? This is atomic physics. I dare teach. Trespassing my limitations, I do teach in this area. Therefore, if I am wrong at any place, I always welcome the experts in this field to give a critical comment on this. At what point I have made any mistake, and if I do so, I promise I will have another video to rectify that. Right now, see, this is the Lyman under low resolution, no Zeeman, one line. There is no external field. But in the presence of non-zero external field, this is external field strength is 0, this is not equal to 0. That means Zeeman. Under that, you see P sub cell has 3 orbitals, P plus 1, 0, minus 1. And in the presence of external field, there will be 3 different levels, which was one level having same energy, degenerate, it will be non-degenerate. And I have told you that S electron, 2L plus 1, L is equal to 0 means there is only one state. It will not be split into more energy levels. So S has only one orbital and therefore one state. P has 3 orbitals which were of same energy, but in the presence of external field will be of 3 different values. And S orbital has no other, because 2L plus 1, L is equal to 0 means only one state, that is 1s. So one transition energy in the absence of field will be converted to 3 transition energies with 3 different, transition energy values. This one is the middle one. This corresponds to the middle line, and this is the lowest energy corresponding to higher wavelength. For example, this is the higher wavelength, and this is the higher energy corresponding to the lower wavelength. So there will be 3 lines corresponding, one to this, the other to this, and this one, the middle one, corresponding to the middle line. So this is a triplet. This is L alpha line. The Lyman series first line is giving a triplet, and you will be astonished that the H alpha line of Balmer series, the first line of Balmer series, is also giving a triplet. How? There are so many possibilities. You might be wondering that why 2p to 1s? Why not 2p to why not 2s to 1s? What has happened to 2s? There was another subcell, 2s, which is of lower energy than 2p. What has happened to that? Now we shall be knowing just after a bit that many transitions are ineffective, infructuous. They will not lead to any detectable peak because the probability factor, the intensity factor is so low that it will escape any detection. So those are called forbidden transitions, and some are allowed transition. In spectroscopy or in quantum mechanics, we have selection rules. That selection rules tells about the probability of transition, the intensity of radiation that is emitted. Intensity, not energy, intensity. If the intensity is very poor, then we will not see any line. So those which have got high intensity, we can see a line. And therefore, we will know that S to S transition, I mean, where L is equal to 0 in one cell and the other cell L is equal to 0, that is forbidden transition. Therefore, the only possibility left is the 2p to 1s transition. First cell has no other subcell, but second cell has two subcells, S and P. So 2s to 1s is forbidden transition. We'll know about that. This is coming under selection rule. Now, the most important thing is the H alpha line. Under magnetic field, it will be again giving a triplet. How? Because there are how many possibilities? 9 possibilities. In fact, there are 15 possibilities. Because the D, there is a 3D to 2P transition. All other transitions are forbidden. You can say 3D to 2P. Yeah, sorry, 2S is forbidden. I'll tell you why. 3D to 2S is forbidden. 2p to 2p forbidden. 3s to 2s is forbidden. So all others are forbidden transitions. But 3s to 2p and 3p to 2s, they are allowed. But I'll tell you that transition energies will match, will be identical with these 3 different transition energies in the transition from 3D to 2p. Now see, D has 5 subcells, and in the presence of external field, it will be giving 5 different energy levels. 2, 1, 0, minus 1, minus 2. They will be all non-degenerate. And similarly, P will be giving 3, 1, 0, minus 1. Now, the maximum transition energy where delta M, change in magnetic quantum number, is, say for example, this, supposing this is minus 1 minus 0, that is minus 1. So the maximum energy will be when delta M is equal to minus 1. In this case, you find that the change in magnetic quantum number is minus 1. Always change is considered from the destination minus the initial. The target where it is reaches, the final state, minus the initial state. So minus 1 and this is 0. So the change is minus 1. All these, so they belong to one category. The transition energy is same because the gaps are same. The gaps are same between the sublevels. Gaps are same. So if delta M is fixed, minus 1, all of them, this is going from 0 to minus 1. This is going from say 2 to 1. So 1 minus 2 is minus 1. This is going from 1 to 0. So 0 minus 1 minus 1. And this is going from 0 to minus 1. The minus 1 minus 0 is minus 1. So all these 3 belong to one category of energy. There are 3 transitions, but the energy is same. Exactly same. So the line is same. And the other one corresponds to delta M is equal to 0. So this is from minus 1 to minus 1. This is from 0 to 0. This is 1 to 1. In all the cases delta M 0. That requires intermediate energy difference. So this energy gap is lower than this. And finally, all these 3 is corresponding to delta M is equal to plus 1. Right? So this is the maximum energy, intermediate energy, and these is the minimum energy. And these are only 3 transitions. But the transitions are 9, no doubt. There are 9 transitions. The other transitions out of 15, because 5 into 3, 15 possible transitions. So other 5 transitions have been discarded due to selection rule. I'll tell you what is selection rule. many transitions are disallowed, forbidden. So they have not been taken. But only these 9 transitions which are allowed, which gives detectable peaks, detectable lines or emissions, then they belong to 3 transition energies. They belong to 3 different transition energies, hence 3 lines. You understood? Although there are 15 transitions between 3D to 2P, 6 are forbidden, 9. Out of the 9, they belong to only 3 categories of transition energies, right? So let me do that. A single Lyman series line, first line due to transition of electron from 2p to 1s, this one, the first one. One line is split into 3 equally spaced lines in presence of magnetic field. It's a normal Zeeman effect. This is because the p subcell is split into 3 equally spaced non-degenerate levels, +1, -1 and 0. 2s to 1s transition. I told you that 2s to 1s transition is forbidden due to the restriction in the selection rule. We'll be talking later. Note that we have assumed a 0 spin condition here. That means we have taken low resolution condition. Either it is a singlet to singlet transition, which we have not considered. There is a pair, but the transition is occurring like helium. So it is going to hydrogen level, but with the same spin. So the pairing is continued, is sustained even in the excited state. In that case, spin has no effect, and moreover, this is low resolution spectrometry. Zeeman, no doubt here, but here low resolution, so the spin orbit coupling effect will not be observed. So I'm reading it out. The resolution level of the spectrometer is low, at which spin orbit coupling is not observed, right? Normal Zeeman effect in the Lyman alpha transition. So I have already told you this is a repetition. Under low resolution condition, one line splits into 3 equidistant fine lines, a triplet under external field. Note that hydrogen atom has a spin due to an unpaired electron, but the spin orbit coupling is not observed at low resolution. Since it is a very complicated issue, chapter, aspect, I have repeated several times, and at the end of my next video, I will be concluding, where you will be participating with me. Selection rules. Now, before we wind up, we go for the selection rule. Now see how far we are to go. This is the last. This is the last. These are the, we are almost at the end of our program. Almost, right? This you already know. So we are happy that we are going to close. Now, what are the selection rules? Those are stipulated for transitions. During electronic transitions, the probability of transition indicates whether a particular transition can produce detectable spectral line having high intensity or not. Yeah, transition is occurring, yeah, but whether it is a probable transition to produce a detectable peak or not. The transitions involving any 2 principal quantum numbers. Principal can be 5 to 2, can be 8 to 2, 8 to 1, that is allowed. From any higher transition, higher principal quantum number to any lower principal quantum number, the transition is allowed. Delta n can be 1, 2, 3, 4, anything, right? The following selection rules are applied to know the allowed transitions which produce high intensity lines for normal Zeeman effect where there is no spin orbit coupling. When there is a spin orbit coupling and also there is Zeeman effect, that is anomalous Zeeman effect, that will be considered separately. There we will have another quantum number that is a mixture of L and S, the orbital quantum number and the spin quantum number. We amalgamate, we blend them together to have another quantum number called the J quantum number, right? L plus S is equal to J. We'll talk about that later. And we have separates, selection rule for J quantum number when there is a spin orbit coupling. But here, no coupling or no detectable coupling, as the resolving power is very, very low. Understood? And the most important selection rule is the transition involving delta L, the change in azimuthal quantum number delta L, small l, is plus minus 1, that is allowed. 0 is not allowed. So therefore 2s to 1s, 3s to 2s, 2p to 1, 3p to 2p, 4d to 3d. So where del L is 0 is not allowed. Even del L 2 is not allowed. Only plus minus 1 is allowed. Don't ask me why. I'm not going to give a video or lecture on the transition rules, the selection rules. I'm sorry. And the restriction for magnetic quantum number should be 0 and plus minus 1. Any transition with magnetic quantum number change, del M, either it will be 0 or it will be plus minus 1, not plus minus 2. Plus minus 2 is disallowed, called forbidden. This makes the direction of electron spin unchanged. This is the consequence is, supposing an electron is here, this is clockwise spin, this is anti-clockwise spin. It will remain as anti-clockwise. When it will excited, it remains the conservation of spin direction. The spin quantum number will be conserved. So I'm not going to discuss the details about this. You must know only this. That is the selection rule for delta L, delta M, and delta N. These three. And obviously del S, there will be no change in spin. You just forget about this, right? Now see, we shall not discuss here the reason behind these rules here. Forbidden transitions will be when del L will be 0 or 2 or 3. And forbidden transitions will be that in which delta M is plus 2. Can be 0 or plus 1 minus 1, but not plus minus 2 plus minus 3. For LS coupling transitions involving the J quantum number, which we have not yet discussed, there the transition and selection rule in advance I am telling you, delta J will be 0 or plus minus 1 are allowed, with exception that J0 to J0, from higher level J0, P level J0 and the S level J0, that is not allowed, forbidden, even if delta J is equal to 0. 0 minus 0 is 0. But that particular exception, J0 to J0 transition, is disallowed, to be discussed later. Now, same thing I have repeated here in a very systematic manner. First talking about the subcells, because third cell has 3 subcells, S, P, D, having azimuthal quantum number 0, 1, 2, and second cell has 2 subcells, SP. Let's see which are allowed, which are forbidden. This 3p to 2p is allowed, del A is equal to 0. And this is 3s to 2s, again del A is equal to 0. And 3d to 2s, del L is equal to 2. So 0 and 2, they are forbidden transition. And which are allowed? 3p to 2s is allowed, del A is equal to 1. Plus 1 or minus 1 doesn't matter. I have not written sign, because always from the final state to the initial state. So S is equal to 0. 0 minus 1. So that will be minus 1. Doesn't matter. Plus minus 1. Similarly, 3D to 2P allowed. We took that in our H alpha line. 3D to 2P. That is allowed. And 3S to 2P allowed. 3p to 2s allowed, and 3s to 2p allowed. In all these cases, delta L is either plus 1 or minus 1, and 3d to 2p allowed. These the values are same. Therefore, this and this, when delta L is 1, their values are same. So I have taken any one which is the one which has got the maximum number of orbitals. So I have not taken, I showed you there the Zeeman effect for the H alpha line splits into a single line, splits into a triplet. There are 9 transitions, out of which 3 are the different transition energy values, right? So I have shown only this 3D to 2P. These 2 I have not shown, because these 2 transitions, they fall into the 3 transition energies that we had from the 9 transitions, right? Now this is no magnetic field, 2p to 1s, This is just an example, whether it is allowed or not. 2p to 1s is allowed because del L is equal to, this is L is equal to 0 and then del L is equal to 1. This is 0 minus 1. This minus 1 is minus 1. So this is allowed. But this is also allowed because when this 2p level will be split into 3 orbitals which are varying energy. So degeneracy has been lifted. So this is 2s to 1s is disallowed. I have not shown that. When I have already told that 3s to 2s is disallowed, 3p to 2p is disallowed. So also 2s to 3s is disallowed. I have not shown that. I have seen 2p to 1s is allowed because delta L is minus 1 and the 3 orbitals in the presence of magnetic field, all these 3 transitions are allowed because del M either 0, minus 1. So this transition del M is equal to 1. And this transition 0 minus 0 is equal to 0. So that is not the restriction in the Zeeman effect. Normal Zeeman effect is not that. The anomalous Zeeman effect will have a restriction for the J quantum number. It's not the J quantum number we have not yet discussed. Now, so from plus 1 to 0. So 0 minus plus 1. So that is again minus 1. So this is 0 minus 1. So that is plus 1. So plus minus 1 and 0 is allowed. There is no possibility of 2 here. Change del M 2 is not possible. All belong to the allowed category 0 or plus minus 1. So we got 3 lines. 3 lines in Zeeman effect. Again, I'll tell you, don't worry. Don't go away anywhere. So let us solve this problem. Which of the following transitions are allowed, which are forbidden? Tell me. Answer. A. 2s to 1s. L is equal to 0, L is equal to 0. Is it allowed? Del A is equal to 0. It is forbidden. 2s to 2s. 3p to 2p. 4d to 3d. That is allowed. Forbidden. B. 2p to 1s. Yes, allowed. Because del L will be equal to, in this case, del L is equal to 0 and 1. So this is equal to minus 1. This is allowed. And C. 3d to 2p. This is the famous one for which we get a triplet out of 9 transitions. Yes, it is allowed. It is also del L is equal to 1 minus 2 is minus 1. So D. 5d to 2, whether it is 5 to 2 or so far as principal quantum number is concerned, del N can be any value. So all are allowed. But D to P is allowed. This two doesn't matter. D to P is most important. This is L is equal to 2 and this is L is equal to 1. So 1 minus 2 is minus 1, so allowed. And this 5D to 2S, no. 5 to 2 is allowed. But what about this? So delta L is equal to 0 minus 2 is equal to minus 2. It's forbidden, not allowed. And F. 5p to 3s. Tell me. SP, they're allowed. This is 0 minus 1 minus 1. Whether it is 5 to 3 or 5 to 2 doesn't matter. So it is allowed. And finally, 6p to 4f. 6 to 4 is okay. But F is delta L. F is 3 minus 1. 3 minus 1 is equal to 2. So not possible. Plus minus 1 is the allowed change in azimuthal quantum number. So it is forbidden. Right? Now we are almost at the end. Normal Zeeman effect in the alpha Balmer series, H alpha of Balmer series. I told you that there will be 15 transition between 3D to 2P. Now there are 15, 3 plus 3 plus 3. Another 3 I have not done because there are 5 levels here, 3 levels here. 5 3s are 15 possible transitions, out of which 6 have been discarded. I have not shown them. They are disallowed. They are forbidden. I have the ones which are allowed are taken. Here del M 0, I have already told you. these transitions which involve the intermediate transition energy where del m is equal to 0, and these three belong to the same transition energy value where del m is equal to, here these three, del m is equal to -1, -1, -0, -1, and the minimum energy will be where del m is equal to +1. All of them belong to a single transition energy, these three single, these three single, so only 3 lines. This corresponds to the -1 category where the energy is maximum. Here this is the wavelength is minimum. Supposing this is the minimum wavelength, and from right to left we are increasing in wavelength, and this is the intermediate energy, intermediate wavelength, and this is the minimum energy where del m is equal to +1 where the lambda is maximum. So there are 3 lines which are equally spaced. Since these are equally spaced, and this the middle one, this is the least energy difference, this is the intermediate energy difference, this is the maximum energy difference. So there are 3 transition energy, 3 lines. Am I not repeating? Am I not boring you? If so, let us proceed. Same thing I have done again. So this is the orange line, single line from 3D to 2P. So this is the higher energy transition corresponding to del m is equal to -1. This is del m is equal to 0, del m is equal to +1, and you have 3 lines. Higher lambda, lower lambda, mid lambda. 3 lines. Because other 6 transitions have been disallowed. And tell me why the 3s to 2p I have not shown here. Only, this is 3D to 2p transitions have shown, but the other allowed transition is 3s to 2p and 3p to 2s. Though are allowed transitions, their transition energy values match with the 3 transition from 3D to 2p, so I have not separately shown, rather the one which is more complicated, which produces 15 possible transitions, out of which 6 are discarded on selection, selection rules point of view, and 9 were taken, and out of 9 only 3 are the different energy transition energy values. Right, same thing. So we come to a close of this part, and you definitely give a pause, give a rest, and immediately start watching. After a break, take a cup of tea, or if you are not a tea taker, you are a student, tea is bad, I'm sorry, I withdraw. Take a glass of water, hot milk, and you watch the next. So to conclude what we did, we learned there are 2 types of fine splitting. Fine splitting, fine lines can be possible in two possibilities. One, without magnetic field, that is due to LS coupling. That happens only under high resolution spectrometer. Even if there is a net spin, is not observed under low resolution. And in high resolution, yes, in the absence of magnetic field, you have a splitting, right? In some cases 2, in some cases 5. I have not told you of 5, only I have told you of the L alpha, just introduced. The details I will tell you in the next video. And in the presence of magnetic field, it is Zeeman. There are 2 types of Zeeman. One, without LS coupling, no spin effect, low resolution condition, Zeeman. That will produce, for L alpha, it will produce 3 lines, Px, Py, Pz, and all are allowed transitions. And the H alpha Balmer series also produce 3 lines, because there are 9 transitions, 15 transitions. 6 are discarded. Out of 9, the transition energy values are 3. Again, 3 different transition energies, 3 lines. Right. This is normal Zeeman effect. And we shall next in video study 2 things. The details about LS coupling without magnetic field, once again in details, the J quantum number, and how spin orbit coupling is taking place in presence of the magnetic field, so that the multiplicity of the spectral line is increasing further. That will be discussed with the final conclusions and some self-assessment question. Bye bye.